Hello! We're still on functions, and we're coming to the close of the chapter. And we've been talking about functions and how the different ways you can represent a function, whether it's ordered pairs, a graph, an input-output table, mapping diagram, words, or an equation. And so we're taking that, looked at functions, and of course the equation. Now we're going to look at linear functions versus nonlinear functions. So basically what we're doing is looking at things that are aligned versus things that are not aligned. And so that's what 5.5 is about, comparing linear versus nonlinear functions. Okie doke. So a nonlinear function, a linear function, remember, has a constant rate of change. And it's in the form y equals mx plus b. So a nonlinear function, it's going to be vocab, so my kids, this is going to be pink. Nonlinear, I almost put equation, function. And what it is, it's the graph of a function that does not have a constant rate of change. Graph of a function that does not have a constant rate of change. Now we're going to look at other ways of figuring out nonlinear functions and figuring out if they're graphs or not. We're going to be looking at nonlinear functions other than graphs to figure out if it's a nonlinear function. My words got all backwards on that. It must be a Monday, and it's the Monday before Christmas break. Yes, I got some Christmas ears going. These are the new ones this year. Little sparkles. They're really cute. I don't know if I've worn them all right, but the bow's crooked. My sister's got them for me, so thank you, Sarah Amber. Okay, here we go. So that's pink. So remember, linear function has to have a constant rate of change, meaning your slope must stay consistent and constant, same, between each point. Now, a nonlinear function, you can't have a rate of change. The rate of change only applies to things that are linear. So that's good to keep in mind. Here we go. So example 1. My tongue is tied today, but that's okay. So we're going to figure out, I'm looking at problems over here. So we're going to figure out if the table, linear or nonlinear. And we're going to explain it. Now the explanations, guys, they don't need to be crazy long. They don't have to get super wordy. Just keep it simple. The KISS syndrome. Keep it simple. Silly. Some people say it's stupid, but I don't. I say silly. Here we go. So we're input-output table. Let's go. Values of x are going to be 3, 6, 9, and 12. Your outputs, 40, 32, 24, and 16. So when you are figuring out if a table is a linear or nonlinear function, you could make these ordered pairs and plot the points. And if it produces a line, then you know it is a linear function. But what's even faster is just finding how things are changing. So remember, we're finding something, the rate of change, and if it's constant, it's going to be linear. So we're going to find how x is changing and y is changing. And when you find the change, you're looking to see what x does mathematically, either adding or subtracting right now. Next chapter, we're going to figure out if things are being multiplied. But for right now, it's just adding or subtracting. So you're going to ask yourself, what do you do to 3 to get to 6? And hopefully you said plus 3. And you can do this every time. And let's say you had an input-output table with inputs all the way down here. You would have to find this change all the way down. I'm going to talk about why here in a second. So for 6 to 9, you are going to add 3 again. And 9 to 12, add 3. So that's good. That's good. Now we're going to do the same thing over here. So same thing over here. 40 to 32. I just repeated myself. It really must be a Monday. Oh, goodness. 40 to 32. What are you doing mathematically to 40 to get 32? So you're finding this change, and you are going to subtract 8. Another way you can do this, you can go 32 minus 8. Does it get you 24? Yes, it does. And you can do the same thing all down. 24 minus 8. Does it get you 16? Yes, it does. So you know that change is negative 8. Now, since this change is all the same, and this change is all the same, you know that this table represents a linear function. Now, here's why you need to do this for all your inputs and outputs. Let's say, you have a table that has 12 inputs and outputs, and it's plus 1, plus 1, plus 1 all the way down, and you're like, gosh, I don't want to do this. And let's say that very last change between, the 9th and 10th input was plus 0.99. Well, 1 is not 0.99, so that does not have a constant rate of change. And so you've got to do this work all the way down because it takes just one small change to throw the whole table off. So that one change right there, that would make this a nonlinear function. So it's super important that you find the change all the way down in your input-output table, regardless of how many inputs and outputs you have. It may seem silly, but you need to do that. So now your explanation. Well, you can get specific. As x increases by 3, y decreases by 8, so rate of change is constant. You could say it's a linear function because the rate of change is constant. But I want you to get specific, so I want you to talk about how x and y change. So as x increases by 3, y decreases by 8. You could say, so rate of change is constant. Okay? And you do the same thing every table you get. So let's do another one. So let's go x and y. So remember, if all the change here is the same, and if all the change here is the same, then it's going to be a linear function. So let's do one over here. Let's go values of x is 1, 3, 5, and 7, and 9. And then your outputs, 2, 11, 33, 66, I don't know, 88. Okay, now let's find the change. So from 1 to 3 mathematically, we're going to add 2. And from 3 to 5, you're going to add 2. From 5 to 7, add 2. And from 7 to 9, add 2. The changes in x shouldn't be too bad. You should be able to see that and just go, okay, we're adding 2 or we're subtracting 1 or whatever it is. Now on the y, so 2 to 11, you're adding 9. From 11 to 33, you're adding 22. You still have to continue. 33 to 66, you're adding 33. And 66 to 88, you're adding 22. Okay. The change in x is constant. That's good. The change in y, it is not constant. So even though you have 2 changes that are same, that doesn't matter. If you have one change that's different, it's going to tell you the whole table is a non-linear function. It just takes one change to throw it off. Now, if you had to explain this, as x increases by 2, how would you describe that? You don't want to say y changes by 9, then 22, then 33, then 2. You don't need to do that. So I'd say something like, as x increases by 2, y changes by different amounts. There you go. You could also plot these. You could make these order pairs and plot them. So it would look like a line. It would dip, go up, dip again. Okay. Rate of change is not constant. Remember, rate of change is specifically slope. Slope only pertains to linear functions or linear equations. Let's keep that in mind. All right. All it takes is one little change to throw it all off, but you need to find the change all the way down as I'm repeating myself again. Okay, we're going to do the same thing now, but with graphs. So we're figuring out if it's linear or nonlinear, And now we're going to give you graphs. So I'm going to change this example 1 to example 2. Make that super simple. And let's draw some graphs. So remember, line versus not a line. Don't overthink this. Okay, first graph. I'm just doing 3 all the way around, my kids. And let's go. This is a function you're going to do later. This function is in Algebra 2, by the way. Okay, now we're trying to figure out if this is linear or nonlinear. Is this a line or not a line? Guys, do not make this harder than it has to be. Is this a line? And remember, some people may go, well, it's a curved line. A line, by definition, is the shortest distance between 2 points. And the shortest distance between 2 points is straight. So that's why if you say a straight line, it's redundant. But this is not a line. So it's nonlinear. Kids seem to make this difficult, and you don't need to. Nonlinear, if you had to explain why, the graph is not a line. Make it easy. Graph is not a line. You don't have to make things difficult. So let's go this one. Let's go graph that looks like that. Is it a line? Yes, it is. So it's linear. Linear function. If you had to explain why, the graph is a line. But remember, there's one line that, although is linear, it is not a function. So the graph is a non-vertical line. Don't forget about that vertical line, x equals something. What happened to all my light in here? Okay. And then we can have one that looks like this. Remember, don't overthink this. Just make it easy. Is it a line or is it not a line? Not a big deal. Don't overthink it. And we just did this function. This is an absolute value function, so A is actually negative. So that tells you that the graph is opening down. So is this a line? This is where some kids are like, yeah, no, yes. And the reason why some kids say yes is because they're looking at this going, well, it's made up of line pieces. When in actuality, do lines bend? Lines do not bend. So even though this absolute value graph is made up of line, if you want to call them pieces or line segments, whatever, they're not even line segments, but the graph bends. Lines don't bend. So even though this part is straight, it's still not a line. It is nonlinear. And we just did this, so you know that this is an absolute value graph. An absolute value is not linear. It's absolute value. You say the graph is not a line, something like that. Okay. Example 3. Oh, I forgot to change table to graph right here, so don't forget to change that to graph for example 2. Whoops. But example 3 is going to be equations. So what we're doing today is we're looking at linear versus nonlinear functions in tables, in graphs, and equations. So example 2 is supposed to be example 2 graphs. I forgot to change the graph part. And example 3 is equations. There we go. I got all the titles correct. Let me scroll down some examples. Okay. And what I want to know is which one of the equations is a nonlinear function. So I'm going to change this up completely. Equations. Which is nonlinear function? Which is A. So I'm going to give you 4 equations, and we're going to figure this out. So A is y equals 4.7. B, y equals pi x. C, y equals 4 over x. and dy equals 4 times quantity x minus 1. And so when you are looking at equations, remember you are thinking about y equals mx plus b. Because a linear function is the graph of a non-vertical function, but it has to be written in the form y equals mx plus b. So that's what we're looking for when we are talking about equations, linear versus nonlinear. So let's look at A. Y equals 4.7. Most of you guys are thinking, well, that's a solution. But remember, y equals 4.7, that has 0 slope. And that is the graph of a horizontal line. I almost said vertical. Horizontal line. So yes, this is a linear function. If I had to explain why, equation is in y equals mx plus b. Because remember, slope is 0. But it's there, because 0 times x is 0. B, y equals pi x. Don't overthink this. Pi is a number. 3.14, blah, 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 on and on and on. It's irrational, but it's still a number. You could still graph this. So y equals slope of 3 something times x. So this is a linear function. Y, the equation is in slope-intercept form. So I'm just going to leave that explanation for down here. Same thing. It's linear. Now y equals 4 over x. Normally you guys see y equals x over 4, and I would have you rewrite that as 1x over 4, and then to make it even simpler, 1/4 with the x next to it. But you guys ever see x on the bottom? Have you seen that much? No, we haven't. So if we don't know if this is linear or nonlinear, so how about we wait on this one and go down to this one? That's what I would do. Okay, y equals 4 times quantity x minus 1. Hopefully you want to distribute. So we have y equals 4x minus 4. Is this in that form? Yep, it is. Even though we had to distribute, it still ended up being in slope-intercept form. So linear, and your reason, equations in slope-intercept form. So let's go back here. So we have linear, linear. We're still not quite sure on this one. You know, we were like, ooh, I'm going to take a guess here, but we're going to wait. But then we know this one is linear, and it's asking which is a nonlinear function. So this is nonlinear. And by the way, you cannot have x in the denominator. It's not going to happen. If you have x in the numerator, it's good. Then you can rewrite that as 1 over 4 times x. So this is your non-linear function. And if you had to explain why, guess what? Not in y equals mx plus b, also known as not in slope-intercept form. So there you go. Even though we weren't quite sure here, like with x in the denominator, that's not, we don't normally see that. We continue with the next one, and then we're like, okay, I know that's linear, and these other two are linear, so this one's got to be nonlinear. But just know that you cannot have your variable in the denominator. Okay. So that's 3 ways we've looked at linear versus nonlinear functions. Tables, we want to find the same change in x and in y, it's linear. If not, it's nonlinear. For graphs, line versus not a line. Don't overthink that. Equations, it's got to be written in slope-intercept form. There we go. If they gave you ordered pairs, graph them. That's what I would do. And verbal, I haven't seen many examples written in verbally, but all you'd have to look for is x and y changing by the same amounts, and then you'd be golden. So that's it for today. Coming up next, arithmetic sequences. We'll catch you later. Have a great day. Be kind. Bye.